Is that starting it?
Yep, that will be the first words on it.
Okay.
Are you sure you did it right?
Yes.
Is it like, does it have the red light?
Yes.
I am an expert.
Peril.
Chris, that's not recording. I swear.
There's a red dot. There's the universal sign for record.
I can't wait to watch this movie.
I'm gonna cut it.
Chris, you suck.
I'm gonna start it with a star wipe.
This is Chris's low budget version of Stat 5060. All right.
Is the cam version.
So,
The investors didn't come through.
right, it's just a shaky cell video.
Yeah.
Used to have friends who were big into
Should we put
getting.
this?
What's up?
Should we put this?
Okay. That's fine.
Had friends who were big into like pirated like movies and stuff like that. Like, what? I would pay $7 to watch this in a theater where it's an actual experience and not to throw up because of some weird like shaky hand cam to see, you know, Fast and Furious 7 or something like that.
Yeah, adds to the experience.
Yeah, you gotta see The Rock.
Right.
Full HD.
Right. Okay. So, I've got assignments. Laura got those back to me. I haven't been able to go through, work through them, and get them scored yet, but looks like things were pretty much on point in terms of that stuff. Only thing I would say quickly is as you're going through, again, making sure people are doing a nice job, and I'm throwing, you know, bonus points your way if things are nice and organized. We go through and find stuff, everything's included, and things along those lines. In terms of your hand calculations, make sure that you're going through and laying those out clearly. Again, if something's gone wrong, wanting to go through and be able to see where that's gone wrong. If you just have the start and the end and nothing in between, I don't know how we got from point A to point B. It's hard to go through and provide feedback on sort of where an error was made. And if I can find kind of where things are, I can give partial credit, right? Back up, sort of mistransferred something or something. It's not a big deal. You did the process right. I can give you most of your credits or most of the value for that. But if it's just, here's where I started, here's where I ended, it's kind of a black box thing. So I can't go through and do stuff. So it's in your best interest to go through and make sure that's laid out, try and make sure everything's clean, give you extra bonus points for that. But we'll try and go through and get. No one here, you guys are all not going to UDCT, is that correct? Okay, cool. Nothing on this set will necessarily, you'll need to go through and start with the next set. So you should be good to go. I'll get these scored back to you, just so you have them in your possession as soon as I maybe want to get back from the conference. Show of hands, who's started or at least started to look at the next set? Okay, good. Any questions or anything like that you've run up against to this point?
It's quite a question yet, but it might be helpful to, like with all the formulas involved for linear contrast, I think I had a note within my notes about like which one is most beneficial for us to use when we do our hand calcs.
For hand calculations, and we'll walk through this today when we start out, just go ahead and use the t-test, the one with the crystal Pepsi next to it.
Okay.
Because what we're going to end up with is when we developed the procedures around contrast, and we're only just scratching the surface. If you wanted to get deep in, and particularly for people who do like primarily like COG, social, experimental types of designs, like getting into the nuts and bolts of sort of specific designs and where you're pulling error terms from contrast and things like that, this is a really involved area, kind of a lot of esoteric stuff that goes on. We're just kind of giving you a general rule for, in general, kind of how things can go wrong. And so for the original procedure where we were calculating Fs with the 1 degree of freedom test with sum of shadows, of course, contrast and stuff like that, that's all assuming a balanced design and everything's working out appropriately. As soon as we don't get that, then we have some problems and things like that. So that t-test is going to be the way that SPSS is calculating those. It's going to be just a more generic way to go through that. And I'm not going to ask you to calculate. I give you a big formula for how SPSS is calculating contrasts with equal variance not assumed. You don't need to worry about that. I'm not going to make you crank one of those out by hand. That's just to show you. I always get nervous if I'm running something and it's a black box and I don't know exactly how it's calculating something. I like to be able to double check and say, is this all working out the way I think it should be? And so that's what that's for, so don't worry about that. Okay. Other questions with set 6? Okay. What?
I think, sorry, I have another one related to that. With
Yeah.
the formula for T critical, I think in the problems that you asked us to do a done SIDAC correction.
Mm-hmm.
With the like T critical formula, it's T.
Like stop you right there.
Yeah.
Yeah, stop you right there. Okay. With the done SIDAC and the bond for running.
Yeah.
And I'm sorry, I just because this seems like common knowledge to me, and I recognize it's not. What do we with our bond for running and our done SIDAC correction? What are we adjusting? What's the correction we're making for that?
Alpha.
Just the alpha. So the alpha is the only thing we need to do. So what you should do is go through for those contrasts and plug in whatever the t-test that you do, the test statistic you get for the contrast, and which degree of freedom do we use for the contrast? Remember? Is it the degrees of freedom for the number of people in the groups that we're using?
The error.
The error, exactly, right? And this is the idea behind running these contrasts within the context of a good ANOVA design, right? We're assuming that we've got equal groups, equal cell sizes, that we haven't had violations of homogeneity, variance, and things like that. And the idea is that we can then capitalize on the total design, even though our contrast might not include all the individual cells, right? And so what we end up doing is pulling our degrees of freedom for the individual contrast from our sum squares error term from our overall ANOVA. And what does this do to the power of the contrast relative to if we were just comparing, say, cell 1 and 2? It increases it. Why's that?
We have more degrees of freedom in our error.
Yeah, and if we have more degrees of freedom, what does that do to our critical value?
It's gonna slide it, I guess, down
Yeah.
to the left.
Yeah. Down to the left, so the north is up, you know how it goes.
Yeah.
Yeah, it's exactly what's going to go. It decreases the threshold for going through and doing this, right? And so this is why, if we have a design where we're having unbalanced design, particularly a markedly unbalanced design and violations of homogeneity or variance, what we end up doing is we lose a lot of power because we can no longer actually, we probably can't rely on classic contrast procedures because they're using sum squares error term for the overall ANOVA. But if we're concerned on whether that sum squares error in the overall ANOVA is a good representation of all the different cells, right? Because if I don't violate homogeneity variance, my assumption is that group A, group B, group C, and group D functionally all have the same variance, right? And if we have equal cell sizes across all of them, then that sum squares error term becomes just a nice general term to go through and look at all of our stuff. Use degrees of freedom associated with that, that's cool. But if we've got big violations of homogeneity and variance, and we've got wildly unequal cell sizes, probably what we need to do, at least for pairwise tests, is just fall back on independent sample t-tests if we have violations and concerns and things along those lines. And when we fall back on those individuals, paired sample, or those independent sample t-tests, just for our pairwise comparisons, we're running those at degrees of freedom for whatever, how many people we have in cell 1, cell 2, -2. So we're losing power, right? We're getting penalized for having violations. Now the upside is we have more confidence that that's an appropriate test. Downside is that we're not able to capitalize on the full design.
Independent samples is super lame.
Independent samples is super lame? Why is
I
that?
don't know, it's just like not as cool as like
Independent sample, like this, it's sort of the basis of mean-based comparisons. Everything generalizes to single sample. We're gonna have, it's not alt enough for you. We'll go through and talk about post hoc tests is about the same thing here too. So, all right, let's jump in then, and Nick, fantastic. Any other questions with that said at this point?
I don't think so. Thank
Okay.
you. It's helpful.
Okay, cool. And I'm gonna be away, but if you have questions, and you guys are working on stuff, fire off an email. I'm happy to go through, like, I'm invested in you, so knowing what you're doing and making sure that you got this under control. So if you have questions, just let me know. Okay, so we're gonna go jump in and we're gonna do sort of contrast. So pull up your output for planned contrast, and then we've got a slightly different set, same idea, but the set we're going to be using is this one-way ANOVA planned contrasts. Okay. So the idea here with our one-way ANOVA, we had the question we had was whether our diverse set of participants would respond similarly to this affective film that's supposed to prime positive emotion, right? Now in our overall, our omnibus ANOVA example, we had a group of individuals identifying white non-Hispanic, black non-Hispanic, and then a non-specific other group, which is not a good way to run research, but for in terms of doing group-based stuff. Here what we have is a much smaller study, right? And what we've got here is the same idea. We've got a video that we're administering to a diverse group of participants. But this time we have individuals who are identifying as white, as black, as Hispanic, or Asian. Okay, so we've got 4 distinct groups from different cultural, racial, ethnic backgrounds. 6 individuals in each cell. So we've got a nice balanced design. And what we're doing is, instead of valences in the last one, what we're doing is we're just rating amusement, again on a 0 to 8 scale. Okay? And so thinking about this as a smaller pilot study of going through and seeing if people are responding similarly to this emotion crime. Okay? So we're not going to worry about going through and screening this. It's a really small sample, but for the purposes of demonstrating our contrasts, this will suit our purposes. So what we're going to do, we're going to go first, and we're just going to go through and just run our overall ANOVA just to remind us all how to do that. So we'll go analyze, compare means, down to one-way ANOVA. Click on that. We have our categorical race variable following the factor, amusement as our dependent list. Okay. And then what we're going to do is we're going to go to options. We're going to hit descriptives, homogeneity of variance test, and our Welch's test here. Okay. And then we can click means plot. Go on. Okay. And we'll go through. You guys hit paste. I'll hit OK. All right. We get our initial output here. Right. Chris C., tell me what you're seeing. Tell me what we're seeing in this initial run here.
We have equal groups, which
Yep.
is nice. Anything else? The numbers are within what we'd expect.
Yep. Generally, we can't. Oh yeah, we got them in max. So yep, those are
min-max.
looking good.
Looks like just based on the means that the Hispanic group has the highest. Is there anything in particular you want me to look at?
Nope, okay, so just looking there, and then so yeah, with our descriptives, this can kind of do just kind of a general thing. So it looks pretty good, right?
Yeah.
What about do we have evidence here of violation of homogeneity of variance?
No.
Yeah, how do you know that?
Because for the test of homogeneity of variances, none of them turned out to be under 0.05.
Okay. Yeah. And so what we're looking at primarily is our means-based comparison here, right? But the idea being that at least with this sample, our homogeneity of variance test is looking like these data are at least generally consistent with the null hypotheses of equal equal variance across the respective populations. Okay. What would be the only maybe caveat that we would have in interpreting this Levine's test? This isn't anything about the Levine's test specifically, this is just to a general methodology. CJ, how many people do we have in each cell?
6.
6. Do we expect this Levine's test to be terribly powered? Yeah. And so this is what I would be thinking of. Like here, I'm not too worried about it. If I'm looking at the standard deviations and we go through and square those standard deviations, that would give up some variances. So that's what's actually being compared. There's nothing that looks wildly out of whack in terms of that stuff, but always wanted to recognize that here, always want to be careful in terms of, sometimes we'll see people say, oh, well, I ran a comparison against this group of 4 and this group of 7, and I found no significant difference, and so these two groups are equal, right? There's a lot of stuff wrong with that statement. What's maybe the biggest thing that we should be concerned about? You haven't goddamn power to test any of that. Like, the difference would have to be so massive in order for this to flag as statistically significant in a group of 5 and a group of 7. The test of the significance test is functionally useless. It doesn't do anything, right? And so the only thing that I would be careful of with a small sample like this is they say, oh, we don't have any concerns with homogeneity of variance spec. Well, we don't have that many people in there, right? So I'm not sort of putting a whole lot of faith in this, right? So I might want to go through with a small sample, just look at my variances, make sure that they're reasonably about the same size, right? But here it's not an issue, but just want to have that in the back of your mind. If I find something that doesn't reach traditional threshold for statistical significance, and I'm looking at side samples of less than 10, right? I'm not super shocked that nothing came up, right? So I want to go through and do a visual check and just make sure everything's looking good, okay? So, looking at that, that's looking okay. Alicia, what about our omnibus test here? What are we concluding based on our omnibus test of differences in means across these groups? That there's a difference there somewhere. Yep. And how did you make that determination? Yep. If I'm looking at my p-value for my test, right, for this omnibus test, it was just saying that we have some evidence, and again, that these data are generally inconsistent with the null hypothesis of equal amusement ratings across these groups, right? Is it strong evidence? Not terribly strong, but with only 6 people in each group, I mean, the problem is there's a lot of weird stuff that can go on in small samples, right? And this is where when we run into replication crises, right? Like in the 60s and 70s, this would not be a weird study to see. And then we start to make strong sweeping conclusions about, cell sizes of 6, right? So we would want to be taking that into consideration as we're interpreting this. But at least these data are suggesting that at least there's something there. We would have a better sense of if there's anything truly going on, if we've gone through and actually screened this and see if there's someone way the hell out here. We're not going to worry about that now, but again, taking all this into context when we're making interpretations about stuff. Okay. So all this is looking good. So it looks like, and here's our means plot, right? So we've got, again, this makes things look a bit more dramatic than they actually are. The scaling's kind of scrunched down. But at least it looks like we have some evidence of potential systematic differences going on in terms of this group. So switch over to the next page of your handout and see what we've got now is because we have we have evidence from our omnibus. We're taking a traditional approach, right, where we want to see evidence of potential differences in that omnibus test before we move ahead into our contrasts. As we talked about before, some people make arguments that we don't need to worry about the omnibus test. I think some smart arguments about that. But for this purpose, we're going to go through and say, okay, we've got that out of the way. So now what we want to do is go through and look at some specific contrasts here. Okay, and so we have three specific predictions, three linear contrasts that we've specified here, okay? So my first hypothesis is they're going to be more responsive than my non-white participants. And in this case, we're saying the majority minority. Okay? Again, because the concern is like sort of, this is a film that has white non-Hispanics actors in it. Are we seeing greater responsivity to people who look like us, let's say? Okay, and so what we need to do for our first hypothesis is, if this is our contrast, we need to come up with our weights. Okay, what's the first thing we need to do when we're identifying our weights? So we've got group 1, people identifying as white, group 2, people identifying as black, 3, people identifying as Hispanic, group 4, individuals identifying as Asian. Okay. So how many people are included in this first, how many groups are included in this first contrast? All 4, okay? And so how are we going to set our weights? So we have, we go through, we go white, black, Hispanic. Okay, so all 4 groups are being included in our first contrast. Okay, we see how are we going to go through and calculate our contrast here, or assign our weights?
So 1 for white.
Okay, 1 for white, and how did you get that?
Just because that's one of the things.
Yep, that's just the 1. Okay, and then how many groups do we have left in the other comparison?
3, so 1/3, negative 1/3 for all of them.
Exactly. So negative 1/3, negative 1/3, negative 1/3. Okay. And why negative?
Because it has to add to 0.
It has to add to 0. Why not make this negative 1 and that positive 1/3 for each one of those?
Because we're expecting the white participants to be more responsive.
Exactly, right? We're expecting participants, our white participants, to score higher in amusement. And again, sort of based on our social theory, we're expecting these people to identify more with the actors, and so then sort of incrementally report higher levels of amusement because, hey, I identify with you and we look alike, and I can kind of empathize with your situation a little bit better, right? So our other groups, negative 1/3, negative 1/3, negative 1/3. Take negative 1/3, negative 1/3, negative 1/3, add those up, that's negative 1, 1, we've got a linear contrast here, right? Absolute value of adding these up is going to be 2, gives us a standard set. This is looking pretty good, okay? All right, second hypothesis. White Hispanic and white non-Hispanic participants will be more responsive than black participants, okay? So how many groups are we considering in this contrast?
4.
Okay. So we've got 3. Okay, there we go. Who's not being included in this contrast? Okay, so we get for hypothesis 2, 0. Okay, what are my other weights? What are my weights going to be for my? So who's in my first group of comparison?
White.
My white non-Hispanic and my white Hispanic participants.
Yeah.
Correct. Okay, and so what's my weight? What are my weights going to be for those 2 groups? Half and half, right? Half and half. And for my individuals, my participants identify me as black.
Negative 1.
Negative 1. Beautiful. Okay.
I think you.
Oh, did I? Oh, oops, yep. Thank you for the catch. This is something that you'll need to make sure that you're doing in SPSS appropriately, because if you forget what group is which, things will get all scrambled up. Okay, perfect. And then hypothesis 3, I'm going to be saying black participants will be less responsive than Hispanic or Asian participants. Okay. Nick, how many groups am I comparing here? 3. Who doesn't get included in this?
Did you say white Hispanic or just Hispanic?
Yeah, Hispanic, just Hispanic and Asian.
Oh, then white.
Yeah. 0 here. And for my black participants, what's the weight here?
1.5. Or it's the inverse. What we just did.
Okay, so
I don't have
Oh, you don't have it?
I don't think I have the right one.
Oh, sorry.
That's okay. Can you,
Okay.
sorry, can you
Yeah,
say
yeah.
that?
So I'm saying black participants will be less responsive than Hispanic or Asian participants. So I wait for,
So they're one.
you gonna be one?
Negative one.
Negative one.
And then one half, one half.
And one half.
And one half.
Okay. So do people see how we set up these weights? Okay. Now the one thing that we'll see when we get into SPSS is pretty limited in terms of the number, how precise that you can get. We're going to run into an issue. CJ, what's 1/3 in a decimal?
133.
Repeating, right? And so what's going to happen is if we go 0.33, 0.33, 0.33, if I add 0.33 and 0.33 and 0.33, does that give me 1? Nope, it doesn't, right? And so SPSS is going to give us an error and say, hey, it doesn't sum perfectly. And what you're going to get, the value of the contrast is going to be a little bit off because not everything sums to 1. Alicia, when you were running this in Stata will allow you to do that if you just carry it out in 7 decimals. It just sort of calculates that appropriately. And so we'll see a little bit of a difference here, but just kind of be aware that SPSS is doing this. How could I go through, what weights could I set so that I didn't run into this problem?
.33334.
Well, I could mess with it and do that, right? And then that's going to give that one group a slight, a little bit heavier rating. What if I go -2, -2, -2, and this is 6? That'll do it, right? Now the value of my contrast isn't going to be in the scale of my units. It's going to be something different. But those weights will give me a more precise test because I'm using whole numbers. It's going to do functionally the same thing. Same thing here. I could make this -2 and that 1 and that 1. The statistical test is going to turn out. The problem is the value of our contrast, if we're using a standard set, is the actual, like the real difference in the average of these 3 groups versus this group. And so we can interpret that as just a literal difference between those groups, which is kind of nice. If I set up my contrasts so that they're not a standard set, then that starts to change a little bit. Waiting for posters, but I keep getting alerts about roads closing down, so shut that off. But does this make sense in terms of how we can play around with this a little bit? Okay, cool. So what we're going to do, we're going to go back to SPSS. We're going to analyze, compare means down to one-way ANOVA. And this time we're going to go up and we're going to select contrast. Now, this is kind of not a super efficient system, but what I can do, as long as I know what my contrast values are, I can go through and enter those here. So I go for my first set of contrasts, my coefficients will be 1, hit add, -0.33, that's all it'll let me do, add, -0.33, add, negative, and this is what it'll do, it'll make me angry. I gotta start over, -0.33, add, -0.33, add. Okay, and so there we go. And you see coefficient total is not 0, it's 0.01, but this is as close as we can get if we want to use decimals in SPSS. Okay, so that's my first contrast. Got that entered, and I'm going to hit next. Say contrast 2 of 2. Here we're going to go, what do we got? We got 0.5. Add, we got -1, add, we got 0.5, add, 0, add, okay? And here's my coefficients, sum to 0, right? And I could hit next and go through and do it again. I won't worry about that right now. I'm gonna hit continue, and then I'm gonna go ahead and I'm gonna paste. So it's somewhat tedious in SPSS to go through and hit next and several entries and things like that. But if we pull up the ANOVA command here, I get the pattern for what contrasts look like, right? So if I want to add that last one, I'm just going to copy this line. I'm going to paste it down here. And then I'm going to put in values for the last, my last contrast here. So it's going to be 0, space, -1, 0.5. So this is just an easier thing to just do it in your syntax command and in working through that interface that ends up being pretty bulky. Okay. Questions about what I've done here, how I've set this up. So really the hardest thing about doing this in SPSS is just getting it to run through the, getting your weights put in, but after that it's all pretty straightforward. Questions about this? All right, cool. So let's go through and run this. Take a look back through, okay? Descriptors are the same, homogeneity, nothing interesting going on up here, right? What we'll go through and take a look at, and wanting to, number one, check, always go through and take a look at your contrast coefficients and make sure that your weights are lining up with your groups the way you wanted them to do that. Make sure that that's all, you want to make sure that you're testing what you're wanting to test, okay? All right, but then we can drop down here into our contrast table. What we see is we've got, just like our independent sample t-tests, Chris thinks they're lame, right? I think they're pretty useful. Maybe not the flashiest, interesting thing, right? Is it a little fancy? Equal variance is not assumed. Do we need to worry about equal variance is not assumed in these data? Not really. So we do not have to worry about that. So we're just looking at contrast 1, contrast 2, contrast 3. Okay. First here, we got at the top value to contrast. Nick, what's the value to contrast represent?
It represents the ratio between, or I guess the difference between those two dimensions.
Yeah. So this is the thing. Contrasts, linear contrasts are no different than just our standard old t-tests. Okay. Basically, it's just saying that on average, based on this, we're saying that our white non-Hispanic participants are scoring about a ½ point lower than the combination of our other groups. That's all. I mean, that's all it's saying, right? Here, for the value of my contrast for the second one, we're saying that, what are we comparing? That the combination of my Hispanic and my white non-Hispanic participants are scoring about 1.25 points higher than my black participants. For my third contrast, I'm saying Hispanic and Asian respondents are scoring 1.7 points higher on average than my black participants. So it's just a pairwise contrast is all it is. We're just lumping groups together, okay? And so, Alicia, for my first contrast, I had predicted that my white my participants identifying as white non-Hispanic would report higher levels of amusement as compared to black non-Hispanic, Hispanic, and Asian groups. What is our conclusion based on these data? We would fail to reject them, right? Basically, again, using sort of the language that we've been using up to this point, we'd say these data are inconclusive, right? I mean, if anything, this is with our overall, based on our statistical test, it looks like these data are fairly consistent with the null hypotheses that group ratings of amusement across among white non-Hispanic relative to our other groups is about the same, right? If anything, it's going in the opposite direction, right? But at the end of the day, data are relatively consistent with the null. We can't make any definitive conclusions. It's kind of ambiguous. So we say functionally these days are inclusive. CJ, what about my second contrast here?
The second contrast gives some support for the alternative hypothesis
Yeah.
that white Hispanic and white non-Hispanic participants will be more responsive than black participants.
Right. Okay. So basically, I mean, it's not, I mean, we're not wowed by it, but at least it's kind of impressive though in a group of, well, we're looking at 18 different people here, right? So we are seeing some evidence for the possibility of the combination of our white non-Hispanic and our Hispanic participants rating this film as more amusing than our participants who are identifying as black non-Hispanic. Okay. And then Chris, what about our third hypothesis?
There's sufficient evidence that black non-Hispanics will score lower than Hispanic and Asian participants.
Yeah, right. Yeah, and so in terms of what we're looking at, so looks like we have some evidence in support of our two a priori hypotheses, not for our first one here. Okay. So and so this is good, this is nice, SPSS has gone through, calculated this for us. What are some other things maybe that we would like to add on to this? Yes?
Base factor, S values.
Base vector and S values, right? And so we could go through if we wanted to just talk about strength of evidence. And this is nice where you can pull up our, just drop those p-values in there. And if you want to get specific with p-values, in SPSS, one of the nice things you can do is if you double click on that table, have you guys done this? If you double click on the table, I mean, it reports it to 3 decimals. If it's less than 0.001, it just reads it 0.000. But if you double click on it, it pulls up the actual value. And you can drop that into your S value calculator to get something that's more precise. In Stata won't do that because it's just a copy. But what you can do is in your calculator, if you put in your test statistic and your degrees of freedom, then you're good to go too. Okay, so a couple of different ones you can go through and do that. Okay, so we want to do that. What else do we want to do? Who wants an effect size?
Yes.
Chris C wants an effect size, right? So let's, all right, let's go.
It's important.
It is important. All right. Curious.
I'm feeling antagonistic.
Against t-tests, effect sizes, right? It's like I got a student in one of my other classes who wanted to have a debate about the ethical principle of justice. What I was concerned about. Right? Like, okay. Also took exception to Einstein. Look, fair enough. I guess I don't know. So,
He's just looking for an argument at that point.
Right.
It's a cheap shot. He's not here to defend himself, Einstein.
So what we want to do is first, when we're looking at we calculated the effect size for our, let's not worry about the first contrast because we don't have much of it there, we can do it, but it's a waste of time. For our second effects here, let's start with value by contrast is 1.25. Okay? And remember, our effect size for our contrast is going to be our value of our contrast over some standard deviation of error. Okay? What do we have in terms of our options for standard deviation of error? Yeah, I don't know. So I'll just put it in first. So we use square root of our mean squares error. Nick, can you tell me what this is referring to? Square root of the mean squared error?
The within variance.
Within group variance. And conceptually, what are we thinking about our within group variance as?
It's everything that wasn't accounted for within our design.
Right. Everything that's not accounted for in our design and in our data, what does it represent? Anybody remember?
Isn't it like the error across all? No, I'm wrong.
Close. Flip it. Within, right? Remember that within an ANOVA design, right? Anybody who doesn't score it within a group, who doesn't score exactly at the mean, what is this? It's error, right? And so basically, our mean squared error is just basically assuming that we don't have, our mean squared error is kind of like just a general, if we have equal cell sizes, and we don't have biased, right? We're taking the sum of squares for cell 1, sum of squares for cell 2, sum of squares for cell 3, adding them all together, sort of dividing them out, and so it just gives us a general error term, right? So if we've got a nice design where we don't have differences in cell sizes, and we don't have concerns about violation of homogeneity of variance, right? We can just go through and pull that, take that mean squared error, which is a variance estimate. We just, it's an aggregate measure of the variability across groups, right? And if the variability across groups is all basically the same, then we're in a pretty good spot, right? So we could use this, right? Our other option is if we could go through and take a look at just the average variance. Okay. So basically what we would do is just take for the groups contained in my contrast, I can just go through and take the average variance of the groups specifically that are in my contrast. Mean squared error, how many groups are considered mean squared error?
All of them.
All of them. Here what we can do is we can just go through and say, all right, well, these are the three conditions of the three groups that are being considered in this contrast. I'm just taking take the average variance across those. Okay. When might this be advantageous in thinking about a standardizer?
Or not including one of the groups.
Okay, and so if we're not including one of the groups, but we can also make an argument that mean squared error is still okay if we're not including one of the groups, because if all our cell sizes are equal and the variances are all functionally equal anyway, it's probably there's more stuff going into this, and so it's this would arguably be kind of a more stable estimate, right? When might we want to go through and start calculating just with the groups within our specific contrast?
We're worried about homogeneity of variance.
If we're worried about homogeneity of variance, right? If we're concerned that so I'm in this specific contrast, I'm looking at white non-Hispanic, black non-Hispanic, and Hispanic groups, right? If I was concerned that I had homogeneity of variance and the variability in my participants identifying as Asian American was much bigger or much smaller than the rest of them, then I might be concerned about using mean squared error, because that's going and it's going to shrink or inflate that, right? And so if I have violations of homogeneity of variance, I might want to go through and just take a look at, so, all right, these are the three groups. I'm just going to take the average variance of those and then just use the square root of that as my standardizer, okay? My other option is going to be pool variance. When might I select the pool variance?
No, all right, no.
Okay.
Unequal samples, unequal
Yeah.
cells.
Yeah. If I have concerns about violations of homogeneity of variance, and I also have unequal cell sizes, probably want to pool that, right? So I have violation of homogeneity of variance, so I don't trust my mean squared error as a good measure for overall variability, right? So I want to just look at specifically the cells that are in my contrast, but I also have an unbalanced design, right? And so what I'm going to go through and do is then extend my pooled variance estimate. So I'm going to have degrees of freedom n-1 for my first times multiplied by the variance plus n-2 for the second group, variance n-3 for the third group, so on and so forth. Just extend that out so we get a pooled variance estimate. And then our fourth option here is just going to be the standard deviation of some control group. Okay. So for this specific study, which one of these standardizers is probably going to be reasonable for our purposes? Yeah.
Mean squared error.
Mean squared error is fine, right? We don't have concerns about violation of homogeneity of variance. We have equal cell sizes, and so this one is probably going to be pretty good. Really, for these data, the only thing that's kind of screwy is just we have really, really small cell sizes without screening. We don't know if something's weird, but at least our statistics are saying that it looks okay to do, right? So what we're going to do here, I'm going to go D equals 1.25. value my contrast over my mean squared error here, going to be square root of 0.908. Okay, you'll see where I got that value from. Just going back into my ANOVA table, and we'll see my mean squared error in my ANOVAs table is going to be 0.908. We just drop that down. And again, if we've got a nice tight design that's balanced and we don't have any weird violations and things like that, mean squared error is kind of a nice general stable term that we can just use as a general error term. Okay? And so if we run this out, we're going to get an effect size here of 1.38. Okay. If we did have violation of homogeneity or variance, or we were concerned, what might be our set go to here? Average variance, right? I've got equal people in each cell, so I don't need to pool anything or weight anything. I can just go through and average that, right? The thing that you always want to make sure that you're doing is you're taking the average of the variances and then taking the square root of that. That's a different number than just taking the average of the standard deviations. Those two aren't equivalent. Okay. All right, and so then for my third hypothesis, the value of my contrast is 1.75. Okay, so D is 1.75 over, once again, square root of 0.908. Going to give me an effect size of 1.84. So again, these effect sizes, we're going to interpret these just as we've interpreted all of our pairwise effect sizes to this point. Here, we're saying that based on these data, we're seeing that the combination of our Hispanic and our participants identifying as Hispanic and Asian are reporting ratings of amusement in response to the film about 1.8 standard deviations above amusement ratings being reported by participants identifying as Black, non-Hispanic, right? I mean, we're kind of just combining these two and sort of going through and getting that together there. So, questions about calculating effect sizes based on these contrasts? Okay. What's the other thing we might want to do here? Charlie, what else do we want? We've been really excited about it all semester. Confidence intervals, absolutely. Okay. So people have this written down if they want to have it written down. Okay, cool. I want to go through and calculate confidence intervals. Okay. And I want to show you this because what I want you to do sometimes is be working smarter and not harder, right? We have statistical programs for a reason. They do a nice job of just plugging, spitting out stuff. If we're smart and we know where to pull it from, we just use that instead of hand cranking things out, pages and pages of hand calculations. Okay. So if we wanted to calculate contrast or a confidence interval around the value of our contrast, right? Based on the very, very small sample of data that we have at our disposal, it looks like that our combination of our white non-Hispanic and our Hispanic participants are rating this amusement film, or this film as about 1.25 points higher than our Black participants, right? But this is a point estimate, right? And given the size of our, or the number of people in our cells, do we expect this to be a very precise estimate? No, not at all, right? So I might want to take a look at the level of imprecision here, okay? So confidence intervals, we're going to calculate our confidence interval as same as we would calculate any other confidence interval. We're going to take mean plus or minus t critical times standard error. Okay. So what we might want to do first is think about what's our t critical going to be for this contrast. What do we have to know before I can get my critical value for my test here?
Degrees of freedom.
Yeah, my degrees of freedom. And Chris, what are my degrees of freedom going to be for this contrast?
It's going to be 17.
What's that?
17.
Okay.
Probably not.
Well, in and this is where we're working smarter and not harder.
Yeah.
You've got a contract, or a sort of a table here that's giving you T statistics and degrees of freedom. What's our
20.
critical value going to be? Or what's our degrees of freedom going to be?
20.
20, right? And where did that 20 come from?
The contrast table.
The contrast table. And where did the contrast table get that value from?
Within groups, degrees of freedom.
Yeah, within groups and degrees of freedom, right? This is the idea. What we're capitalizing on the overall design when we're running our contrasts. And so what we're going to do is, again, we're using degrees of freedom based on my within subjects design. Now, if I have violations of homogeneity or variance, right, then all of a sudden, this is when I have to start sort of maybe taking a different approach, or thinking about, if I'm just looking at pairwise comparisons, just running t-tests on the groups that I'm actually interested in. This is hard to do if we have multiple group contrasts. SPSS gives us corrected tests, which is probably fine. Again, so we can't independently verify that this is sort of the optimal way to do things, right? And you'll see, and it does not assume equal variance. We have adjusted degrees of freedom, right? The 9.11, 8.2, whatever, right? You can go through and get, you can find online calculators that will take decimal degrees of freedom and actually give you a value. You just have to kind of hunt around and look for them. But we don't have to worry about this here. Want to look for a T critical with 20 degrees of freedom. And if we go through and we look at online the test here, we get a T critical of 1.725. Okay, so our 95% confidence interval here is going to be 1.25 plus or minus 1.725 times, what do I need here? Yeah? 0.448. Where did you get 0.448?
The contrast interval for the first, oh, we're in the second one.
Where's the second one?
Sorry. It's 0.477.
0.477. 0.477. Okay. And you'll notice that these the standard error for the second and third degree of freedom, or the second and third contrast, are identical. My 1 is off. That's because my sum of my contrast, the sum of my weights doesn't exactly equal 0, and it throws everything off a little bit there. Okay. But exactly, right? So just going through, we don't have to go through and crank out a hand standard error. We can just pull it off of out of our printout. Okay. And what we're going to end up with then is a confidence interval of 0.43, 2.07. Okay. We do the same thing for our third hypothesis. Same procedure. It's going to end up being 0.93, 2.57. And so we would interpret these the same way. And what I'll do is this is helpful. If I go through and like put together an example of how we might sort of tie this all together and interpret some of this, is that worth sort of me doing? Okay. So what we would want to do is use the same type of principles as we've done up to this point to go through and make interpretations of this, right? Essentially what we would say is we've got, based on the ANOVA test, we have evidence of for differences in the mean values of amusement across white non-Hispanic, black non-Hispanic, Hispanic, and Asian American populations. Individual contrasts, sort of comparison of white non-Hispanic groups against all others would be fairly consistent with the null hypotheses. Just put in stuff, right? Just leave that alone. There's really not much else to talk about there. However, we did find evidence for differences consistent with hypotheses in this one. Difference in ratings of amusement for white Hispanic and white non-Hispanic groups relative to individuals identifying as black, ranging anywhere from an increase of 0.43 point unit increase to 0.07, right? Effect size quite large, you see about 1 3/4 of a standard deviation increase. However, interval estimates quite large, but the difference could be anywhere as low as less than a ½ point difference, all the way up to a 2-point difference, right, on a 0 to 8 scale. That's pretty big. Brandon didn't just want to incorporate this, and then say the same thing for the other one to pull this all together. Basically, nothing unique or special about this. We're just using the same principles and the same sort of approach that we've used to just talk about sort of individual effects going on here. Okay. Questions, comments, concerns about running our contrasts? Yeah.
So if the contrast is basically like how many points of difference something is, what's the effect size of the contrast?
Someone help me out, that's a good question. So value of the contrast is a difference. Effect size is also the difference. What's the difference in the difference? Yeah.
It's the measure of standard deviations difference for the effect size.
Yeah.
Oh, okay.
So if I don't know, if you tell me the value, Chris, you say value of my contrast in this for this effect is 1.25. Is that a lot or a little? I don't know. Absent knowing what that scaling is, it could be something trivial all the way to something really massive, right? Here on a 0 to 8 scale, I don't know if I'm running a study, and one group of individuals are responding to my manipulation on a 0 to 8 scale about over a full unit higher than another group. That's not a trivial difference, right? But if I don't know that, if it's a 0 to 100 scale, meaning on that could change completely, right? And this is why the effect size is nice. It helps provide things within context. I know what 1 3/4 of a standard deviation means. That's a lot. That's really, really big. That's something that's going to be really obvious, right? And so it just kind of helps increase the meaning of this, which is why I put such a big, big emphasis on having you all give me a practical interpretation of what these actually mean. What we tend to do is just default and say, oh, it's small, medium, large, blah, blah, and don't actually think about what this actually means. But literally, for my second half, we're getting close to 2 standard deviations above for the combination of these groups relative to these. That's a massive thing, right? If I'm running an experiment and I'm seeing that racial ethnic differences, sort of like background characteristics, are causing close to a 2 standard deviation increase or decrease in response to my experimental manipulation, I might be concerned about that, right? And that might be something to make a report on too, right? So one of the things that having sort of diversity of our samples is always a concern, right? Sometimes it might not make that big of a difference, sometimes it might. If I'm seeing based on this pilot data that people of color are responding to this systematically different to the tune of 2 standard deviations of a unit difference than some other people, that's going to be something that I probably want to be thinking about in terms of building my interpretations. Questions on any of this? All right, cool. So let's jump in and finish up with post hoc stuff. So we talked last time about general sort of perspectives on post hoc tests. The problem, everybody loves post hoc tests, particularly Tukey. Everybody really jazzed about Tukey. Tukey's good. Tukey's good if we need Tukey. The problem is we need to be considering carefully, do we need to look at all possible pairwise comparisons, right? Because this is what our post hoc tests generally are doing. They're saying we're looking at all possible combinations of all possible 2 groups within our design. A lot of times that's not going to be interesting or make any sense. Sometimes it will, and if it does, that's fine. If it doesn't, what we're doing is we're paying a premium on power for correcting for tests that we don't care about, that we're not interested in interpreting, and when they do come up, they're kind of a pain in our ass because now we have to explain why this rando group is different from that rando group when our theory really doesn't give us any idea of why it should be, right? So want to be careful when we're going through that we're not just defaulting to Tukey or post hoc tests. To look at things just to look at things, and particularly if we have a specific set of important comparisons, we don't want to correct for all possible things to test the 2 things that we're actually interested in and making it that much harder to sort of reach effects and things like that, right? Now, when we're thinking about post hoc comparisons, lots and lots of options. we're going to talk about fissures, two-key, a couple of variations of two-key, a scratch, student, and cool run. I don't worry about that. Shafay, I've done it. But there's lots and lots and lots of other ones out there. Okay. So, starting with fissures. Okay. Fissures LSD. This is kind of the classic approach to post hoc testing. Is that once we go through and once we find evidence in our ANOVAs test, right, in our one-way ANOVA, that we have evidence against the null hypotheses there, Fisher's LSD says after that is jailbreak. We can go through and test whatever we want to test, is completely fine, and we're going to go through and we're going to compare each one, run each one of these pairwise comparisons at per comparison error rates. Okay, and essentially what we're doing with Fisher's is we're just looking at independent sample t-tests, right? So for Fisher's LSD, we've got the mean of group 1 minus the mean of group 2 over the top of mean squared error over sample 1, mean squared error over sample 2, and then we're evaluating this against a t-critical with degrees of freedom pulled out of the mean squared error term. Okay? So what ends up happening? So this, everybody identified this as just a independent sample t-test. Okay, what are we, in an independent sample t-test, what are we substituting in our calculation of our standard error from our standard independent sample t-test for our for Fisher's? What goes here in our independent sample t-test? What's that? Pooled variance. Okay, good. This is one thing, sort of Laura made it, this is what something that got people tripped up a little bit on the last assignment. People just put the error variance or the variability for each group in each one of these, right? Remember that for when we're calculating our independent sample t-test, we need to have pooled variance in there is what we're doing. So basically, we're just substituting our pooled variance for our mean squared error. Mean squared error is just a type of pooled variance, right? And so this all works out fine as long as we haven't violated homogeneity of variance. This is the concern, right? Is this mean squared error a good representation of variability across all of our groups? And if it is, we're just going to go through and essentially run independent sample t-tests. Our t-critical is using our t-critical with degrees of freedom error from the overall omnibus test. So if this ends up being sort of a lower threshold than if we were just running our regular independent, if we're just comparing two groups, right? We've got 10 and 10, then our degrees of freedom is 18. But if we've got 10 and 10 and 10 and 10, our degrees of freedom error from the full ANOVA is significantly larger, right? So we're getting some extra power there, okay? So we see that Fisher's is going to be the most powerful of our post hoc testing procedures. The problem with Fisher's is it's criticized for failing to manage our family-wise error rate, okay? So if I've got 4 different conditions, right? If I've got 4 cells, that's giving me 4 times 3 over 2. That's giving me 6 possible comparisons, right? And I take 0.05 times 6, what do I get 0.05 times 6?
0.3.
What's that?
0.3.
0.30?
I think.
Okay. Is that 0.05? No. So my alpha for that set of comparisons is considerably larger than what I would be expecting sort of individual, right? And so if we have a simple design, we only got 3 levels, right? And so we've got 3 possible comparisons. There's an argument to be made for Fisher's to say, well, it's sort of close, or sort of alpha level is 0.15 across the set as opposed to 0.05, but maybe we can do this. But in general, Fisher's is going to be hard to get away with. It's a post hoc test in that it's using terms from our overall ANOVA to go through and test things. The problem is that it's not managing these error rates, and so we have some problems. If it's not managing family-wise error, what are we concerned we're going to do? Yeah.
Reject the null.
Yeah, we're going to make type 1 errors. We're going to be rejecting the null, but we shouldn't be rejecting the null, right? we're going to be capturing things just because of chance. Right? And so this is the concern with fishers. Question about fishers? All right. So then we get into Tukey. Everybody loves Tukey. People don't appreciate, people don't understand Tukey. They don't really hear Tukey here. They don't sort of understand the ins and outs of Tukey. We're going to get you guys understanding the ins and outs of Tukey, because if you do, then you can use it flexibly in ways that are advantageous, particularly when we get into our factorial analyses. Okay? So Tukey and a number of different post hoc procedures are based on the studentized range statistic. Okay? This is a Q distribution. And Q distribution, the Q statistic has a little bit different sort of distribution than our T distribution, things along those lines, although they're directly related. Okay? Our Q statistic, what we're doing for our Q is we're taking the difference between our lowest score and our difference, or our largest score, and the difference between our smallest score in the set. So if I have 4 in a one-way ANOVA, right, I have 4 different groups. Right? So in our example that we went through, we had 4 different groups. What we would do to get our studentized range statistic is we would compare the lowest mean score against the highest mean score. Right? And then we would divide that by the mean squared error term for our overall ANOVA, divided by the number of people in each cell. Right? So this would be the highest score minus the lowest score, if we're using the last example, over the square root of 0.908 divided by 6. Right? Because that's how we go through and get our Q statistic. Okay. But incidentally, we think about T, right? Our T statistic, at least as we were sort of calculating for our fishers, is difference between my two means over 2 times the mean squared error over n, right? Which is essentially just the same thing as square root of mean squared error over n1 plus, right? Oops. This is just a different way to write this, right? So my Q statistic and my T statistic are very, very similar. Basically what I can do is my test statistic, at least using this, is going to be this equal to my Q divided by the square root of 2. Or my Q is going to be equal to my T, calculated using this formula, times the square root of 2. So T and Q have a direct relation with one another. Okay? This is going to be important to sort of remember this. So basically we're just taking the T statistic formula that we used for Fisher's LSD, right? And we can take that and move back and forth between a studentized range statistic back and forth. Okay. People understand, can I see how these two things, there's a relation between these two? Okay. So primary difference between our T critical and our Q critical is we've got values in our Q table based on different degrees of freedom, different number of so basically in our Q table, I think I'll give you a minute, you can grab one of these Q tables. Basically, in a Q table, what we have is we're looking on the column here, we have our error degrees of freedom, right? And over the top is based on R, the total of number of means in our sample, okay? So let's say Nick let's say I've got 4 conditions, okay? And I have, say, 10 degrees of freedom, error degrees of freedom. What's my Q critical for these tests?
You said 4 conditions?
Yeah. 5.77, right? And so Q crit is 5.77, okay? Now if I take 5.77 and I divide it by the square root of 2, what do I get? .08. 4.08. Someone have a T table or a T table set up? Someone tell me what a T critical value is with 10 degrees of freedom. So T critical with 10 degrees of freedom.
I see.
Yeah.
It would be 2.2.
Degrees of freedom. 2.26. Two point two two eight.
Yeah.
It's 5.77 divided by the square root of 2. Is that 4 point? How did this fail? Oh, yeah. No, this make, okay. Sorry about that. Yes. So what is T critical? 7? 2.228. Okay. So for a pairwise test, for a T critical with 10 degrees of freedom, right? So I've got 6 people in one group, 6 people in the other. Okay. What's my critical value if I'm just running a T test at alpha 0.05? The T that I've got to exceed, I have to, my benchmark is 2.288. Okay. But remember, what are we doing with Tukey? Why are we running Tukey in the first place? To correct for multiple comparisons, right? And so at per comparison error rates, my critical value for a t-test with 10 degrees of freedom is 2.28. But if I have 4 comparisons, right, or 4 groups, so I have 6 comparisons, right? What's my new critical value in order to claim statistical significance based on a Tukey procedure? Now it's 4.08. Okay. What we've done is we've gone through, because we're not running 1 test, we're running 6 tests, and we want to go through and control for increasing alpha inflation across 6 different tests. And so if we have to control for that, what happens to our benchmark for claiming statistical significance? It starts to get increased down here, right? So this is a nice way to go through and take a look at the cost of just running pairwise or running post hoc tests, just to run post hoc tests. If I'm just, playing contrast, just like I'm looking at this specific prediction, my threshold to claim statistical significance is 2.288 or 2.228. If I run all possible comparisons in this set, if I'm using Tukey's procedure, now it's 4.08. I have to have a much larger test statistic in order to claim statistical significance here. Okay, so people can see kind of how this is working back and forth. So what Tukey is doing is within the Tukey test, is it's using this Q statistic, but Q has a direct relation to T, and we can move back and forth with this. Okay, you'll kind of see where this is coming from, how this is working out. Okay, so here's a full Tukey table. So we see number of steps between ordered means is just the number of means that we're comparing. Here it's just 2 all the way to 15. And what we can go through, we use this the same way as we would use like a traditional null hypothesis testing thing, right? So for Tukey, from a classic standpoint, we don't actually get a p-value for Tukey. It's just, this is significant at Tukey less than equal to 0.0, or Tukey equal to 0.05, right? SPSS actually calculates a p-value for you, but traditionally what we would do is we would go through and say, I've got 5 means and 60 degrees of freedom in my error term. So my Q critical value is 3.98, and then everything that was less than 2.98, or so excuse me, greater than 3.5. So anything greater than that would be statistically significant at Tukey less than 0.05. Okay. So people understand kind of how Tukey's being. So it's just using a different statistic as like a function of a T. We're kind of getting this because this is going to be important when we start thinking about how to use this flexibly. Okay. So when we're using Q, what we're doing is we've gone through. So the idea behind this post hoc test is that what we've done as an investigator, if I'm using Tukey, it assumes that I've gone through, and I have no a priori hypotheses, right? I just went through and I ran this analysis. And actually, and after I've gone through and ran those analyses, I'm looking at my different means, and in my head, I'm thinking, I wonder if these two means are different than one another at a statistically significant level. So what I'm going to do is I'm CJ and I'm drawing this. I have no high values, right? But after I get it, I've got a one-way ANOVA with 5 different means, and I'm going to go through and I'm going to say, I wonder if this mean group is different from that group, right? Once I've done this, once I've actually looked at my means, the data that I've collected, and I start wondering whether or not X or Y, or Group A and Group B are different than one another, dramatically alters my type 1 error. Why is this? Yeah.
Because it's far more conservative.
Yeah.
I think overall.
Yeah. What am I, so Chris, you're looking at, you run a study, you run your thesis, you have no real predictions on stuff. You're like, I wonder if this group is different than that group. What's probably the reason you're wondering whether those two groups are different?
Because I assume that they are in some way.
Yeah, and what's caused you to assume that they're different based on looking at the
Because
means?
I've just observed that.
Yeah, because they're different, right? What I've gone through is I've gone through and looked at all of my means. And what Tukey is saying is that I've gone through and I've already automatically just ran all possible pairwise comparisons in my head. Not officially, but probably what I'm doing is I'm probably cherry picking the means that are most discrepant, right? So as you're going through, you're like, I wonder if that really low score is different than that really low score. I wonder, let's go just see if this is statistically significant, right? But the problem is I've not gone, what I've done is I've not looked at all of these. I mean, I did, but anything that looks really close, I sort of push that away, like, oh, that's not worth looking at. This is the one I'm really interested in, right? And so for Tukey, what we do is we would go through, and I've got 5 different cells here. So I've got a one-way ANOVA with 5 different groups, and I would go through and order these, the means from lowest to highest, okay? And then what I'm going to do is I'm going to determine the number of steps between the means to be compared, okay? So as soon as I've gone through and I've looked at this, and I've done this in my head, Tukey is saying, you've already gone through and you've run all possible pairwise comparisons, so now we're going to tax you for them, right? You can't just cherry pick which ones you want to look at. You've gone through and looked at all of them, and so now we need to institute a correction for the fact that you informally looked at all possible pairwise comparisons. And so from a theoretical standpoint, this is why this is really important to have your hypotheses laid out before you actually look at the means, because we're human beings and it's impossible to sort of fight against, well, I didn't predict this on the front end. Like, oh, yeah, I kind of forgot about that one. Or, oh, this makes some sense. But that starts to dramatically change our type 1 error. So even if I do only run one comparison, right, the comparison I run is probably this one versus that one. And so it's not fair to compare it at a 0.5 level error, because what I did is I ran all 6 of these and then just picked the one to go through and do. Okay? So what we're going to do with Tukey is we're going to order things up. And then I'm going to determine the number of steps in the classic approach between the means to be compared. So the original Tukey formula would say, okay, what I'm going to do if I'm looking at the difference between 1 and 2, that's going to be just 2 steps or 2 means, right? So we can have R equal 2 if I'm measuring this one versus this one, that's 5. So I would look at a critical value equal to R equals 5. Okay? Then I would go through and calculate my Q statistic here. So I want to go through and compare 1 and 5, right? And so I'm saying that I've got 29 minus 4 divided by 32 was my mean squared error from my overall ANOVA table. Divided by 8, I've got 8 people in each cell. And I'm going to test this against a Q critical is 4.07 at alpha equal 0.05, degrees of freedom 35, and R equals 5, because that's the number of steps that I'm completing here. Okay. People see where we're pulling these values from. So which one, based on sort of what we had saw from the Tukey table, is my critical value going to be higher with R equal 5, or if I were to do it here at R equal 2? Which one, Chris?
R equals 5.
R equals 5, right? The idea is that I've looked at this, and this is I've basically chose the min and the max. And so if there are 5 different means in our group, in my grouping, I'm getting a bigger penalty for choosing the biggest ones versus ones that are nearby. Okay. So again, we'd say that this whole procedure is similar to our classic T t-test, we just don't get a specific p-value here. If we found, so in this case, we would say that our Q statistic is 12.5. That exceeds my critical value for 4.07. And so I would just then say that based on my 2P procedure, that this contrast is the questions about the basic procedure here? Okay. So this is how sort of 2P sort of is done sort of from a classic old school standpoint. But we can start to go through, if we understand what's going on with 2P, we can go through and we can start to manipulate how we can start to do this, and this is going to be particularly important for when we get into like factorial designs and things like that. I've got a post hoc, I want to run some post hoc tests in a factorial design, but as we'll talk about, looking at all possible comparisons is not only not theoretically meaningful, but also not sort of practically meaningful, conceptually meaningful. And so we want to be able to kind of sometimes be able to go through and adjust this a little bit. So one thing we can do with Q is we can just determine a critical t-value necessary to claim statistical significance. Okay. So in this case, let's say we've got ANOVA, got 6 levels in the factor. So we've got 6 total means. And then we say we've got 47 degrees of freedom in my error term in my overall ANOVA. If I go to my Q table, I see my Q critical given alpha 0.05, R equals 6, and 47 degrees of freedom is 4.23. Okay. People see where I got this? Sort of at least in concept. So I just went to my Q value, my Q statistic. I say I've got 6 means, so I'm going to set R equal to 6. I'm going to look at alpha 0.05. I've got 47 degrees of freedom based on my ANOVA table. I'm just going to go through. My Q critical is 4.23. Okay. But then, instead of running a bunch of Q statistics, what I can do is I can take that Q critical and turn it into a T critical, right? So I take 4.23 divided by the square root of 2, gives me a T critical of 2.99, right? Versus if I were to just look at a sort of at per comparison rate, if I look for my T critical with at alpha 0.05 with 47 degrees of freedom, it's 2.02. We're seeing I see an increase. Like I'm needing a correction there for my reduced or my sort of comparisons. So based on my Q, I now have a T critical of 2.99, and then I just run T-tests. Okay? As long as my test statistic exceeds 2.99, I can claim this is statistically significant and 2P correction at alpha less than 0.05. Okay? So what I've done, let's say again, if I've got 6 levels, right? 6 times 5 divided by 2 is 15, so I've got 15 possible pairwise comparisons that I could make in this ANOVA. What I would do is I would just run pairwise comparisons across all 15 groups. Any T that exceeds 2.99, I say it's significant at 2P correction. If it's not, then I say it's not significant at 2P correction. And then I just go through that. You'll see how we've taken our Q critical, our 2P critical value, translated into a T, and then just done what we always do. Comfortable with this? Okay. Another thing we can do is I can determine the difference in means necessary to claim statistical significance. Here we're just using some algebra to go through and take a little bit of a different approach. So here, again, I've got T critical is 4.23 given alpha 0.05, R equals 6, degrees of freedom 42. And in this case, let's suppose our mean squared error is 32. What I can do if my Q statistic for my critical value is the largest minus the smallest over mean squared error over n. What I can then do is I can just rearrange this formula and say the difference necessary for the largest over my smallest is my Q critical times the square root of the mean squared error over n. And then what I just do, so I go through and I say, well, if my Q critical is 4.23, multiply that by mean squared error is 32 divided by 8. That gives me a difference, largest minus smallest, of 8.46. Okay. Then what I can do is then I can just compare any 2 means. I can look at the mean here, mean here. If the difference in the mean exceeds or is equal to 8.46, then that's significant at P less than 0.05 based on my 2P correction. Or at alpha equal 0.05 based on my 2P correction. So again, we're just using 2P to go through and run through some different sort of algebra. Do you want to run a test statistic and just calculate a bunch of t-tests? That could be fine, right? If I but that's a lot of running stuff in SPSS. If I wanted to, I can just take my critical value and my other information. I just calculate how much, literally how much do these means need to differ from one another in order to be statistically significant. With my 2-key correction, I can do that as well. Yeah.
Would you still run an additional like t-test afterwards just to confirm, or?
No, because it's going to work out. Now the whole thing, like this whole premise, this whole thing is based on the classic 2-key. Because this is what we're using, what are we assuming?
Equal variances?
Yeah, equal variances, right? As soon as we start to have different sample sizes, we start to have different variances, this kind of falls apart a little bit, right? Because for all of this, we're assuming that comparing that group 1, group 2, group 3, group 4, group 5, group 6 all have roughly equal variances. So I can just use this mean squared error term as representative of the within group variability of each group. But as soon as that doesn't become tenable, then all this stuff kind of starts to fall apart from a classic 2-key perspective. Okay. All right. So to get back talking, 2-keys honestly significant difference texts. There's a number of different variations on 2-key. 2-keys HSD. 2-key HSD evaluates all pairwise comparisons at maximum values of QR. Okay. So all comparisons that we're making are using the critical value for sort of the max distance between these two. Okay. So with 5 factors, all means are treated as if they were 5 steps apart. And what ends up happening is we fix vandalized error to be equal to alpha across all possible pairwise comparisons here. Okay. So with 2-key HSD, if I have 6 groups, I'm fixing those 15 comparisons so that the set of comparisons does not exceed alpha 0.05 across all of these. And so what we can then do is we can compare Q critical if I want to calculate Q statistics. I can compare against T critical if I want to use independent sample t-tests for each comparison, again, assuming that I haven't violated homogeneity variance and I have equal cell sizes and things like that. Or I can look at the minimum difference if I want to compare raw differences across means. If I'm doing this by hand, any of these are equally viable, and I'm going to get the exact same answer. It's just sort of a procedural issue. So benefits of 2-keys HSD, one of the most popular, good protection against type 1 error. 2-keys probably the most common thing that we'll see. No one's going to yell at you for using 2-key. Okay? I mean, 2-key is kind of like a magic word, right? If you guys like, yeah, I used 2-key corrected this, people are generally pretty jazzed about that, right? Drawbacks, loss of power in cases where not all pairwise comparisons are interesting, right? Basically what I've done in this, let's say I've got 6 levels to my one-way ANOVA. I'm correcting for 15 comparisons. If I'm not interested in 15 comparisons, I'm giving up a ton of power just to go through and test maybe the 3 I want. What I should probably do is think about this on the front end, say these are the 3 I'm interested in, and then just compare those 3 at per comparison error ratio, maybe a slight correction using Bonferroni or Dunsitic or something like that. What I don't want to do is then, after the fact, after I've looked at things, then decide what my hypotheses are, and now I've got to go through and correct for 15 tests, and I'm probably going to miss stuff. I'm going to lose a lot of power there, okay? And so basically we're correcting for comparisons whether we want to look at them or not. So questions about 2-keys HSD? Okay, some variations on 2-key. 2-key Kramer, right? Classic 2-key approach, and again, more relevant to like experimental stuff, right? Like so these measures or these methods developed within the context of sort of nice randomized designs where we can assign people to different groups and things along these lines. But as those of us in sort of other areas of bastardized sort of perfect sort of randomized control groups, right, and trying to use the same type of thing, then we run into problems where now all of a sudden we don't have equal cell sizes, right? I'm comparing a substance use group of 20 people versus a bunch of other undergraduates who don't have substance abuse problems, and there's 100 of those. 2-key starts to break down, right? So 2-key Kramer accounts for unequal samples. So basically, 2-key Kramer is just taking the mean of the groups that we're comparing, and taking that times the mean squared error divided by however many people in group 1 plus mean squared error divided by how many people in group 2 divided by 2, take the square root of that. Tukey-Kramer is the default in SPSS, right? Tukey-Kramer defaults to Tukey with equal sample sizes. So when you say Tukey in SPSS, it's talking about Tukey-Kramer. Same thing with Stata. Tukey is Tukey-Kramer. Okay. We also have James-Howell. Okay. This is what if we have concerns about both unequal sample sizes and unequal variances, which happens quite a bit when we're going through and looking at stuff. James-Howell goes through and makes a correction similar to the Behrens-Fisher approach to our independent sample t-test. What we've done is we've gone through and I got a new critical value W that's based on Q with a correction here. We've got a different adjusted degree of freedom. Again, you don't have to worry about running these. I won't have you do these by hand. But if I'm in a situation where I run a one-way ANOVA, and I found that I have an unbalanced design, and I also have concerns about violations of homogeneity of variance, or if I wanted to go through and run post hoc tests, I should probably be requesting James-Howell. It's just a variation on Tukey that it adjusts for this. Other post hoc tests, student Newman Cools. I'm going to cross this out. It'll come up. We're not going to worry about it. But basically, student Newman Cools goes through and uses an R value for Q critical as the actual distance between each one. So my critical value for the comparing adjacent means is going to be lower than my critical value for means that are quite far apart. Okay? Again, more powerful than HSD because we're not comparing all things against the same critical value. As my means start to get closer together, the critical value starts to drop, it gets easier to meet. And so we get a little bit more power, but less control over type 1 error. Student Cools also assumes a balanced design. Chaffee. Chaffee is kind of exotic, right? Most of you see Chaffee, someone's like, oh, Chaffee, what Chaffee does, Chaffee based on Tukey, but Chaffee provides a correction for all possible comparisons. Okay. CJ, if I'm comparing for, what am I doing different if I'm measuring for all possible comparisons versus all pairwise comparisons?
Pairwise comparisons are going to have greater power.
Yeah, why?
Less variance. Or well, they're going to use the, this kind of takes out a variable, I guess, when you use the same pair.
Okay. So how many, so I've got 3 groups. How many pairwise comparisons can I make? 3. Okay. How many possible pairwise, how many possible comparisons can I make? So I got 1 and 2, 1 and 3, 2 and 3. Then I could also run a contrast with 1 against 2 and 3. I could run 2 against 1 and 3. And I could run 1 or 3 against 2 and 1. Chaffee's correcting for all of that, right? And so what this ends up being is extremely, extremely, extremely conservative. So if all I'm wanting to do is go through and compare for all pairwise comparisons, Chaffee is not your guy. Because what Chaffee is doing is it's correcting for all possible pairwise comparisons and also all possible contrasts. This is an extreme. You know why people use Chaffee? Because they already went through and looked at the stuff that they wanted to talk about and found out it doesn't make a difference. And then I want to use Chaffee because it's sexy, and then I can go through and say, if I saw that in paper, I bet why you don't need to do this. This is not necessary, right? But if you really just wanted to get in the weeds and start comparing all possible like pairwise comparisons and contrasts, just that you thought you could just think up in your head, Chaffee might be a way to go through and do that. And then done it again assumes a balanced design, but with done it, what we do is we have just some reference group, and then we just run through and compare all other groups against the reference group. Okay, so kind of a different procedure based on a separate table, nice test. It's just kind of unique, right? You have to have a situation where I have one control group, and then let's say 3 other experimental groups, and I want to run each one of the comparison experimental groups against the control control, then I've done it is nice, right? Because it doesn't make sense for me to compare experiment group 1 and experiment group 2 against one another. What I just want to do is compare each one of these. Done it is a nice, it's more of a specific, it's a more boutique post hoc test for situations where this starts to come up. Okay. Other thing that's happened, so that I added this in, I went through and uploaded an Excel worksheet. And this is a job coming product based on some of his books. This is an old thing, an older version of it. But what's nice, and starting to think about this, is if I have a bunch of post hoc comparisons, particularly if I have a bunch of them, it kind of starts to get hard to keep this all straight in my head. Sometimes it can be nice to just have something that's a visual representation of kind of what's going on. If you download this, and this is the last sort of tab on the Excel sheet, it's way at the very end. Basically, you just set up a graph where we can go through and insert your point estimates and your upper and lower limits here, and it'll just populate a plot for you, right? This is a nice way to just go through, particularly if I have a bunch of post hoc tests, go through and just look at sort of where my things are landing. This is kind of cool, right? We can see, well, we've got comparison 2 and 4 are, so we can claim evidence against the null hypotheses here, just based on our confidence intervals. 1 just kind of ekes across a little bit, but it's just a nice way to graphically represent kind of what's happening with stuff. So when I say in this next problem set, where I say I want you to go through and plot out things using the ST worksheet, that's what it is. Okay? So it's easy. You just drop in your point estimates and your upper lower limits that you've already calculated. It just provides a nice visual. Just make sure that you include a footnote at the bottom. Basically take this, take a screenshot of this right here, plop it into your write-up, and that'll be good. Just let me know what comparison 1, 2, 3, 4, 5, and 6 are, however many you've got going on. Okay. So again, just a nice tool for just giving a nice visual for what's happening with things. Questions on this? All right, so which one of these tests is best? It's going to depend on a lot of context, right? If I've only got, my tests are planned in advance, only a few comparisons that I'm going to want to make. Use just independent sample t-tests, Bonferroni Dunn-Siddick correction if I have a small set of planned comparisons. Or if I just want to say, hey, these are things that Chris sees run a study. It's a decent design, right? So I want to go through it, but he's like, these are the 3 things. There's 12 different comparisons I can make, but these are the 3 contrasts that are the whole reason I've done this design. And so I'm going to run each one of these specific contrasts at per comparison error rates. It's completely fine, right? You can correct Bonferroni Dunn-Siddick if you like, but that's really up to you. If we have test plan advanced, more complex comparisons, right? Use linear contrast, again, Bonferroni Dunn-Siddick. What you shouldn't do is say, I have 15 planned comparisons. No, you don't. Stop. You can sort of go down through and sort of think about what specifically you want to take a look at. But if you have a large set of exploratory post hoc tests or 15 planned comparisons, now you probably need to go through and start making some correction. 2-year variance of that generally going to be the thing that's going to be probably the easiest to make arguments for. Questions on this? How are you feeling about this? Is lots and lots and lots of options, right? Like, boy, everybody loves options until they have to decide between options, and then it starts to get kind of overwhelming. Is anybody feeling overwhelmed by this? Feeling overwhelmed? Okay. Let me know. Okay. So what you need to do in this, as you sort of go out in the world and start doing things as amateur statisticians, needing to be aware of, okay, these are the options available to me. Which one of these things makes the most sense? What's going to be sort of things I need to be thinking about is really the big thing that as you're going through and taking a look at things is think, do I have balanced design? Do I have violation of homogeneity or variance? Is it reasonable for me to just start pulling that mean squared error term, using that as representative of all groups in my data set? If that is, awesome, then I can do a lot of this cool stuff that maximizes power. If it doesn't, oftentimes what I end up doing is falling back on independent sample t-tests, and I have less power. That's sort of my penalty for having unbalanced designs, variability, and sort of kind of all over the place, right? So it's just going through and having a game plan before you jump into this about how I'm going to address these issues, right? And definitely advantages of that, thinking that beforehand, before you get your data. It's easy to say, oh, well, let's just get the data and see what happens. Have a game plan, then stick with that with adjustments based on, well, I thought I was going to have equal variances, but I didn't, or I thought I was going to have equal cell sizes, but I couldn't get people in this group, right? So I'm going to make through, but these are still the we've done to take a look at. And then if you want to add a bunch of exploratory stuff afterwards, cool, just label these things as exploratory. Like these are the things that I want to look at. This other stuff is exploratory, so we're going to tax the hell out of it in terms of power and things like that. But these are the things that are really most important to me. All right, cool. Let's go through, take a break, and we'll jump back in when you guys get back. But in getting to things that are more relevant and better use of your time as opposed to less relevant and not a good use of your time, post hoc comparisons in SPSS are just going through in a one-way ANOVA. You just hit post hoc, and then you just check the boxes that have the post hoc test that you want, and then you hit run, and then just spits them out. I mean, that's about all there is to it. So I have a screencast video that just shows you sort of how to go through and do that. So we'll just leave post hoc tests and how to request those in SPSS to that screencast video and jump into Factorial ANOVA, because this is where things start to get a little bit more complicated in terms of conceptually and procedurally how we want to go through and move forward with comparing means-based analyses using a number of different factors. So again, we're going to go through conceptual overview of kind of what we're trying to do with our factorial designs, talk about main effects and interactions, calculations for our factorial ANOVA, and then finish up with our effect sizes, confidence intervals, follow-up tests, and things like that. Okay. So at this point in time, what we've done, we've talked about one-way ANOVA to look at a single categorical variable, the relation between a single categorical variable and continuous outcome. Okay. Continuous outcome, one categorical variable, a number of different levels, and thinking about our one-way ANOVA as an extension of our t-test, right? We're just looking at 3 more groups. T-test, again, just a special case of ANOVA. You'll see sometimes people running pairwise comparisons in ANOVA. That's fine. You just take that F value and you square root of that, it gives you a T, right? Interchangeable there, okay? But what happens if we're interested in multiple factors, right? I'm not just interested in one categorical variable in relationship to some outcomes. I'm interested in looking at multiple categorical variables. We could run multiple one-way ANOVAs, right? But we've got issues with alpha inflation, again, as we had before. But then probably the most important, right? If I'm just running multiple one-way ANOVAs, I can start to miss effects that are caused by specific combinations of these factors, right? So I can look at differences across sort of racial ethnic background. I can look at differences across men and women. But if there's certain combinations of racial ethnic background and gender that start to have an impact on whatever it is I'm looking at, I'm missing those if I'm just running a bunch of one-way ANOVA models, right? And so our solution is going to be our factorial ANOVAs. What we're doing here is we're incorporating 2 or more factors into the same analyses. So with these are going to be tests that are more efficient than our multiple ANOVAs. We're going to avoid some complications with increased type 1 error, just running a lot of tests that are not efficient. And what we see, and we'll talk about this, is our factorial ANOVAs tend to be more powerful than our one-way ANOVAs. And we'll talk about mathematically why that's occurring at some point in the lecture here. It also allows us to make more confident inferences about effects and generalization and things along these lines, right? What we can start to do is look at whether or not differences across certain levels of some factor persist if we start to go through and sort of look at other variables, conditions, and things along these lines, right? right? So I'm saying, does the effective condition depend on, say, gender? Does this hold, right? I've got an experimental condition, and I've got participant sex that people have been randomized, so men and women have been randomized to different things. I can say, okay, I'm seeing differences across experimental groups 1, 2, and 3. Does that hold still when I control for biological sex, right? And so we start to get stronger inferences from our ANOVA, or our factorial designs, okay? And then probably the most important, why we're running these factorial designs in the first place, is we're able to look at combined effects of multiple factors. We're able to look at interaction effects. And this is where things start to get more interesting and probably start to look more like sort of how behaviors occur in the real world than a situation where sort of outcome on some measure depends completely on this one categorical variable, right? So we get a little bit more nuance. And then giving us greater overall flexibility with regard to experimental design, right? I can say, well, based on my theoretical model, right? Chris, you're looking at something, you're saying, well, sort of this thing, and some relationship stuff, gender is an important factor, right? But maybe gender is an important factor, and then, oh, yowza, how did you do that?
Jared?
Yep.
Yeah, it's a paper towel or something like that.
Yeah. I didn't close it, and when I shook it.
Oh, nice. I was like, did that coffee just explode at random? That's weird. It's like it got a lot of carbonation. Thank you, Nick. Or
Thank you.
Chris.
Sorry about that.
It happens.
Yeah. I like to do when I got like in my kitchen or something like that, like pull out something like the milk or orange juice or something like that. Yeah, you have to throw it.
Yeah, because you put it in the fridge and the lid, you know the lid isn't on perfectly, but you're like, all right, I'll remember that later, it's
Yeah.
fine. And then you pull it out the next day.
Yeah. She
Too
didn't
many
make my
times, yeah.
existence. I'll remember this later.
Yeah.
Or oh, y'all just do this and then I won't forget.
You never
I'm gonna
do.
step out to the restroom real quick,
Okay, I
just to
can- yeah,
clean
yeah.
myself up a bit.
Oh, what? Yeah, Chris is on point. Thank you.
Thank you.
Yeah, you can still step out if you like.
Just so that I can get a little bit of the,
Yeah.
thank you.
Oh, this one. All captured on video.
Yeah, I believe so.
Right? It's an exciting day. All right. So with this experimental design, so it allows us to go through and start to model different factors, right? So for Chris, your stuff, you might have, so we're having individuals being sort of this group, these different experimental conditions, but also we want to account for gender, right? Because that's going to be, we expect that maybe these interactions or these effects might cross with these other things to go through and model that appropriately in our design, okay? So if we're thinking about our factorial ANOVA, again, want to make sure we're straight with our terminology. If I have a factorial design, I have every level of a factor paired with every other level of subsequent factors, okay? So a full factorial design gives us all possible combinations of our independent variables, right? So if I've got condition 1, condition 2, condition 3, and I'm also modeling participant gender, right? Then I'll have men in group 1, men in group 2, men in group 3, women in group 1, women in group 2, women in group 3, okay? We start not having a full factorial design, things start to get kind of complicated. We have to use some more esoteric statistical analyses to go through and get through that. But for a full factorial design, full crossing of everything, it's everything. We're generally going to identify these designs based on the number of levels and the number of factors that are analyzed. So a 2x3 factorial design. Chris's is your hypothetical study. We would identify this as a 2x3 factorial design. We've got two factors. We've got factor A, factor B. Factor A is participant sex. Factor B is experimental condition, right? So I've got factor A with 2 levels, factor B with 3 levels, calling this a 2x3 factorial ANOVA, okay? And again, most appropriate use of this is going to be in straight up experiments where we've got different conditions, where people randomized to we've got experimentally controlled conditions where people are randomized to each cell. That's generally the most appropriate use of these. We've kind of adopted these to use to take a look at pre-existing groups, which starts to get a little bit tricky with some stuff, but we'll ignore that for right now. So within our factorial designs, a cell, again, this is going to be a subsample with for a specific combination of factors. Our main effect, okay? Our main effect is going to be the difference in means across levels of a given factor, collapsing across all other factors, okay? So if I have a 2x3 factorial design where I've got gender and condition, right? What is my main effect of gender referring to?
Whether gender impacts the outcomes of the three other factors.
Okay, that's starting to get into an interaction. If I'm just looking at the main effect of gender, my question is,
differences based on gender.
yeah, do men and women differ, right? The other levels of factor, don't care, right? So my main effect of gender here is going to be irrespective of condition. Do I see overall differences across men and women, right? That's going to give me my main effect of sex. What about my main effect of condition?
This would just be the per condition.
Is condition 1 different than condition 2, given than condition 3, ignoring gender? Okay. And then what we have is we're going to have conditional effects. Conditional effects, you'll sometimes hear these talked about it as simple effects. This is the effect of one factor on our dependent variable at one level of a different factor, okay? So what we have here is effects being conditioned or dependent on the level of another variable or factor. So in this case, this is important to have this straight because these designs can get pretty confusing. If I have sex and condition, okay. My simple effect, so my main effect of sex is going to be, are there differences across men and women? My main effect of condition, are there going to be differences across conditions 1, 2, and 3? My simple effects then is looking at within condition 2, do men and women differ? Within condition 3, do men and women differ? Right? Within men, do we see differences across 1, 2, and 3? Within women, do we see differences across 1, 2, and 3? Those are going to be our simple or conditional effects. Okay? And these are the effects that we're going to start teasing apart when we get evidence of interaction effects. That's when things start to get kind of interesting and cool. But we have to think carefully about how we're going to approach this, what makes sense to look at, so on and so forth. Okay. So, give you a handout. I think, Alicia, do you have a handout to give you? Okay, this is a different one. Hold on to this one. Don't look at this one yet. We got a different one. So with our one-way ANOVA design, remember our example that we had used, looking at test performance based on temperature, right? So we had people working in like 50 degree, 70 degree, and 90 degree, okay? And we found in that design that, and we found that, in that design, we went through and we found differences based on temperature. People in really hot temperatures don't perform well. People in really low temperatures perform well. So baby bear, just right. So that is where people play the best. But if we're thinking about, so I think you're from Oregon, right? Chris C. Maryland? No. Virginia?
One more south.
North Carolina. Okay, yes, let me use you. Yes. Okay. Is temperature the only thing that matters in terms of your overall comfort and performance in North Carolina? No. Yeah, what else is going on? Humidity, right? So maybe what we want to do is look at performance based on a combination of heat and humidity, right? Because 80 degrees feels different in North Carolina than 80 degrees feels in Wyoming, right? 20 degrees also feels different in North Carolina than 20 degrees feels like in Wyoming, right? And so what we might be interested in is looking at the impact of not only temperature, but also humidity in terms of performance, right? And so in this example, right, what we've got is we've got two different factors. We've got factor A, humidity, high and low, and then we've got temperature, 70, 80, 90 degrees, right? And so what we've got here is we can ask, what's the effect of factor A on outcome, right? This is our main effect. What's the effect of humidity on performance, right? We can also ask, what's the effect of factor B on outcome? What's the effect of temperature on performance? And then we can ask, what's the combined effect of factor A and B on outcome, right? Here we're asking the specific impact of combinations of heat and humidity on different types of temperature, okay? Note that each one of these, right, we've got a 2x3 ANOVA here, okay? We've got factor 1 has 2 levels, factor 3 has 3 levels. Identify this as a 2x3 factorial ANOVA, but we're talking about 6 distinct populations, right? And again, when we start talking about populations in factorial ANOVA, these are kind of hypothetical populations. So this is a hypothetical population of individuals completing a task or so, assigned task at 70 degrees and low humidity. This is a hypothetical population of individuals. Like these, let's say we've got 10 people in the cell, these may be the only 10 people who've ever completed this task in this specific temperature, right? But we're talking about hypothetically, if all people were to do this in this condition, what would we expect the population value to be? So remember that each one of these is such an increase in complexity because now we're talking about 6 different distinct populations. We're not interested in the data, right? And we're interested in the data in the sample, but only to the extent that it tells something about the likely score that we would see if we took everybody in the universe, dropped them into this situation, and had them complete this task. So, if we're thinking about our main effects, okay? Main effect of humidity. My hypothesis here, again, because I've only got 2 levels, it's pretty easy to write this out, right? Population mean at low, population is equal to population mean at high. My alternate hypothesis, population mean at low is not equal to population mean at high. And what we're going to do is we're going to go through, we're taking like at the observed variability across our humidity means over the expected variability assuming that the null hypothesis is true. Okay. Sadly, where am I interested, where am I seeing my main effects of humidity in this table?
Your high humidity?
Okay, so yeah, so if I want to look at a comparison of my main effect in humidity, what means am I comparing here?
Oh, you're between, or,
Right here at the end, right?
Okay.
So this is my high and my low, right? So collapsing irrespective of temperature. What's performance look like at low humidity? What is temperature? What does performance look like at high humidity? Okay, we just got this comparison. We also can look at our main effect of temperature. How does performance? So my null hypothesis is that the mean of performance at 70 is equal to performance A is equal to performance at 90. My alternate, I don't have a notation way to say this because there's a lot of different ways I can find differences here, right? So I'm just saying mean performance differs in at least one temperature condition. Nick, where am I seeing my main effect of temperature? Bottom. Yep, down at the bottom, right? So ignoring level of humidity, do we see differences in people at 70, 80, 90 degrees? Okay? And here we're looking at observed variability across my temperature means over what would be expected just based on some random variability. People comfortable with main effects here. So main effects, we're talking about marginal effects here. These are things that are happening in the moments, right? Things start to get a little bit tricky when we get into interactions, okay? With our interaction effects, we're looking at variability across our individual cells within the design. And we're looking for variability that exceeds that that's predicted from the overall main effect. So once we've gone through and we've calculated, addressed differences in temperature, we've addressed differences in humidity, are we still seeing systematic differences that exceed what we can expect accounted for based on our main effects and our interactions? conceptually, when we're thinking about this, what we're saying is that the impact of one factor on my outcome is dependent on the level of another factor, okay? So I'm saying, Siley, if you asked me, right, what's the effect of temperature on, performance? If I have it, I can tell you, but I can't tell you exactly what the impact of performance is without knowing what the humidity level is, because the impact of temperature on performance depends on humidity, okay? So in the current example, interaction effect is going to say, again, impact of humidity on performance impacts temperature, kind of the opposite of what we've said here. So an interaction for humidity and temperature, our null is going to be that the effect of humidity on performance is independent of temperature. Right? It doesn't matter what temperature is. The difference that we're seeing across high and low humidity is systematic, irrespective of how hot it is. Right? Our alternative hypothesis here is going to be that the effect of humidity is in fact dependent on temperature. So I can't tell you what the effect of humidity on performance is. I need to know what the temperature is, right? Because if I don't know what the temperature, I can't describe you exactly the impact of performance, because it depends. We're talking about low temperatures. We're talking about high temperatures. Sort of, I need to know additional information before